This is lecture 25 and we are discussing laminar premixed combustion. So, the first topic we discussed in laminar premixed combustion is about its fundamental property of premixed combustion, that is laminar burning velocity. So, we derived expression for laminar burning velocity, did some calculations, found out how laminar burning velocity depends on pressure, temperature, equivalence ratio, etc. Now, we are discussing some other phenomena in the context of premixed combustion and specifically in the context of laminar premixed combustion. So, in the last class I mentioned quenching. We will start with quenching. Now, quenching is extinguishment of flames, and the way quenching is studied is you can take a tube, for example, and flow a fuel air mixture through the tube, and you can get a flame. And then if you suddenly stop the reactant flow rate, then you would expect to see the flame come back. So, that is called flashback. So, the flame moving back inside the tube is flashback, and the reason we can study quenching like this is, okay, if you take tubes of different diameters, for some tubes the flame which flashes back will not be able to propagate all the way down. It will propagate some distance maybe, but then it would get extinguished. So, that is called quenching. Extinguished means the reactions in the flame will become very low and will get stopped, and you will not see a visual flame. If your tube is transparent, you will see that the glow of the flame, the visual flame zone is going off, and we have already seen that in one of the videos in a previous lecture. So, in that experiment which was recorded on this video, the tubes of different diameters, then a fuel air mixture is flown through the tube, and the tube and the fuel air mixture is suddenly turned off, and then you see the flame coming back. In some cases the flame could come back, propagate all the way down. In some other cases the flame did not propagate all the way down. Okay. So, there was a situation when the flame got extinguished midway, and that we call quenching. Now, if you remember the video again, you will recollect that in those situations where the tube diameter was small, when the tube was narrow, then the flame was not able to propagate all the way down. All right. So, the first thing that we seem to understand from that video is that the flame traveling in the tube has the fuel air mixture, because you are flowing the fuel air mixture, then we suddenly stopped it. Even though we stop it, it still has the mixture in it. It still has the mixture in it, but the mixture is not moving out so much because you have stopped the flow. So, you have a tube which is filled with a fuel air mixture. So, the flame has the possibility of moving down. It was not moving down when the flow was taking place, because then in that case this flame for example was getting its feed of the fuel air mixture, but you suddenly stopped it. Now, the flame has now this opportunity to travel back. Okay. So, that is why that flashback was happening, and we saw that if the tube diameter was small, if this was a narrow tube, then in some cases the flame could not travel all the way back, it got extinguished. So, the first question that we should ask ourselves is why is it happening for narrow tubes? Okay. So, in a narrow tube what changes? Why is it getting extinguished? Okay, the response is heat transfer from outside to inside is more. Outside of what? Outside the tube? But yeah, from the flame. It's actually the other way around. From the flame, heat is going to the wall. Okay. From the flame, heat is going to the wall. So, if you think about the flame, what's the positive thing about the flame? What helps the flame? The fact that there is a reaction taking place, there is a conversion of chemical energy to thermal energy, that is good for the flame. Okay, that helps the flame propagate. We know how a flame propagates. It heats up, the mixture ahead of it, the unburnt mixture, and it also pumps in some radicals, some chemical active species, and then the flame is able to propagate. So, if the reaction is strong, then the flame will be able to propagate. We understand that. But since the flame is extinguishing in some cases, obviously there is something which is not going right for the flame, which is counterbalancing the effect of the heat release that is taking place in the flame. Something which is making the flame weaker. What can that be? And I think you have rightly guessed that this must be the heat loss from the flame to the wall. It is not about heat transfer from outside to the flame, because in any case outside is colder than the flame. Okay. So, we understand that this heat loss is probably doing something to the flame which is weakening the flame, that is lowering the reaction rate of the flame and forcing it to get extinguished. But that does not answer our question fully. My question was, why does it happen for tubes of smaller diameter? It is not, did not seem to happen for tubes of larger diameter.
Because it is getting kind of more resistance and more in contact with the walls.
Yeah, so the response here is that in narrower tube there is more contact with the walls. And the way to quantify that is, of course, to calculate an area by volume ratio of the flame. Okay. So, the flame which I have drawn, just marked here, that flame, if you think about it in more detail, it is like a disc. Okay. So, this thing I am drawing here. So, this is just the flame. This is the axis of the tube. So, this is the tube. This is the flame which is trying to propagate. Okay. So, it is like a disc, we can say, approximately. Nothing is actually like a flat smooth surface in a flame. Okay. It is not, because we remember the videos, it does seem to get distorted, it is not exactly planar and things like that. But we have to do an analysis, we have to simplify things, we cannot take all complications into account. So, we take this as a disc. Now, you can tell me what this is, how much is this? Delta. So, this is the thickness of the flame. We are using the same notation as we used for laminar burning velocity and flame thickness derivation of expressions. So, this is delta, and if we call this tube diameter as d, then this area by volume is what? Area is pi d into delta. Which area are we talking about? Contact area. So, that should be pi d into delta, and the volume should be pi d squared by 4 into delta. Volume of what? Volume of the flame, right. So, the deltas can get cancelled out, pi's will get cancelled out, one of the d's will disappear. So, this will be 4 by d. So, area by volume is actually 4 by d, which tells you something which you must have guessed even before we got this expression here, that if you have a smaller diameter tube, then the area by volume ratio, the contact area divided by volume ratio, is actually going up. Okay. If it goes up, then the heat losses in a relative sense will be stronger than the heat that is generated in the flame, than the thermal energy released in the flame. In some sense it will be stronger. So, that is the whole idea. So, in that context we can understand something about quenching, but we want to go further and also derive an expression for what is known as a quenching distance. The d that I have marked here, this can be called a quenching distance. For a tube, it is that diameter of the tube below which a flame will not be able to propagate. More than that, the flame will be able to propagate. Okay. So, that is called a quenching distance. So, there are quenching distances for tubes, but there are also quenching distances for slots. Suppose you have a slot kind of burner, that means a rectangular cross section, maybe with a high aspect ratio, and through that there is a mixture flowing, and then you have a flame established on the top of that slot. You stop the flow of the fuel air mixture, suddenly will the flame come back, okay, or will it get quenched? So, it is a similar question, similar to the circular tube situation, but you have this other situation when you have a rectangular slot and if you have this, then this distance is d and this is called a quenching distance. So, typically we call a quenching distance even for a tube, we call a quenching distance even though it is actually that diameter. Okay. So, here we call it the quenching distance. So, again the same thing will apply. If you have a slot burner where this width, this distance d is smaller, then the flame will likely to get extinguished. So, you can actually you can again think of a flame and then you can calculate an area by volume ratio, and it will be very easy for you to see that if this distance is smaller, then the area by volume ratio is larger. Okay. Now, we will not even do this slot burner, we will just do a derivation where we have two plates like this. So, it is like open on one side, open on this side and open on the back side, and it is just the two plates, long plates. Okay. So, if they are long, then they can contain a mixture, right, if they are long. So, and then you have this flame here which I am drawing like this, and this again will be delta. Okay. We will call this L and we will call this D, correct. D is the spacing between the two large plates. Yeah, the objective of the analysis that we are going to do is to get an expression for D in terms of something else, in terms of the properties of the mixture. Okay, D is this spacing between the plates gets extinguished. So, we want to determine the limiting value of D, we want to get an expression for D for which quenching happens for the first time. What do I mean by first time? Imagine having these two plates, and let us say that to start with you consider a configuration where the plates are far apart, and you have this fuel air mixture here in between the plates. If you ignite, you expect the flame to go through because the distance appears to be large, and then you reduce it, then you keep reducing it. At one point of time it will not be able to propagate, that is when we call it a quenching distance. So, smaller than that it will of course be able to quench the fuel.
So, here we are not going to stop the flow.
We are not going to, in this example we are just thinking of a situation when you have these two plates and between them you have a fuel air mixture. So, it is similar to a situation where okay, you have these two plates, in here there is a flow going through them and then you suddenly stop the flow. So, then you have a fuel air mixture which is not flowing and the flame is propagating. We are thinking of that situation.
As we are decreasing,
yeah,
at the same time we are also at different distances we are also stopping that flow, and then we are finding out.
Yeah. So, these are all different experiments. First experiment, large distance, fuel air mixture between these two plates, fuel air mixture is not flowing, okay, not flowing. So, how do you imagine fuel air mixture not flowing? You first think that there was a fuel air mixture that was actually flowing, then you stop the flow and now the flame will start coming back and your observation time starts from there. So, that is the first experiment. Second experiment, you reduce the distance between the plates by some amount, do the same experiment as the first one. Third experiment, again reduce the distance between the plates by another amount and then do the experiment again. We keep doing that until the point when the flame gets quenched, and actually your question pertains to I think that situation. We are looking at a limiting case, right. We are looking at a limiting case because once you get quenching, then further experiments with smaller distances between those two plates will also result in quenching. If you want, you can do those experiments, but you are going to get quenching. So, we are talking about a limiting case and we want to do an analysis. The question that was asked was, what is the purpose of this objective? We want to get this D, the limiting value of D, which is the quenching distance, in terms of few things, in terms of the mixture properties or laminar burning velocity or something. If you if you have two plates, if you have a fuel air mixture, right, then D cannot be just one number, one universal value for all kinds of fuel air mixtures. That's not possible. Even for a given fuel, the equivalence ratio of the fuel, that fuel air mixture, suppose you are considering only propane, the propane air mixture equivalence ratio will determine the value of D, isn't it? Stoichiometric mixture will have some value of quenching distance. If it is not stoichiometric, it will have some other value of quenching distance. If you change the fuel, then the quenching distance will also change. So D depends on a few things, right? D depends on the fuel type, depends on the equivalence ratio, maybe some other properties of the mixture, which we'll have to see, right? So we want to get an expression for this. Okay. Now, the analysis that we are going to do is going to be for this limiting case, as I mentioned, when you get quenching for the first time, right? But the analysis that we will do will be good in the sense that it will tell us something about D, what mixture properties D will depend on. But it's going to be a simple analysis because we are just looking at a situation where the limiting condition has been met. Okay, so the limiting condition must be that the heat generation and the heat loss are becoming equal. Okay. So there is this thing going on for the flame. Heat generation is helpful for the flame. What is going against the flame is the heat loss. So we are talking about this limiting situation when the heat generation and the heat loss are equal. If you reduce the distance any further, then the heat loss will definitely win over heat generation. If you increase the distance between the plates, then the heat generation will be able to overwhelm the heat loss. Why is that happening? Again, that area by volume ratio argument. So we are just going to do this. So for our case, it's like a steady situation, sort of. Okay, just taking a flame like what I have shown here and writing heat generation equal to heat loss and then getting an expression for D. But come to think about the video that we saw, the propagation of the flame. Quenching is not exactly a steady phenomenon, isn't it? It must be a transient phenomenon because you get a flame, it's moving, maybe it will move some distance, but it will get extinguished. Okay, so we are not going to deal with quenching in its full flavor. We are not going to deal with quenching as a transient process that is happening. Okay, we are just looking at a limiting situation, some distance between the plates for which the heat generation becomes equal to heat loss and thereby derive an expression for the quenching distance T. Later on, in fact, maybe in today's class if possible, or definitely in tomorrow's class, we will start looking also at another phenomenon which is ignition. So you can suspect probably based on the discussion that we have that in case of ignition will take place in a mixture if the heat generation wins over heat loss. Even the other kind of argument, if you have a fuel air mixture and maybe you have given a spark, you have ignited it, whether that ignition will sustain itself or the flame will get extinguished will depend on whether heat generation can overwhelm heat loss. So that is kind of the reverse thing of what we are discussing today. Today we are discussing the situation when we are looking at quenching. So we are seeing that okay, if we do this, if we reduce the distance any further, then heat loss will overwhelm heat generation. Okay. So ignition will have similar kind of argument, but the point is that ignition also is going to be a transient phenomenon. Okay, you ignite and then you see whether it gets sustained or not, things like that. So there is a process, but we are in case of quenching as well as in the next class probably when we discuss ignition, we are just going to look at the limiting case and ignore the details of the transient nature of these processes. All right, so we want to get D and to get D, we have to write Q dot per unit volume, that is the heat generation, multiplied by the volume of this flame. The volume of the flame is delta into D into L. Okay, now that should be equal to the heat loss. So, heat loss will be thermal conductivity K multiplied by area. How much will be the area? These are two large plates. So, 2 delta L. Okay. 2 delta L multiplied by, there has to be a temperature gradient at the wall. Okay. Now, the temperature gradient at the wall is a little tricky. So, let us see, do I have space here? Okay, I will try to use this space here. Let's think about these two plates, and we have a flame in this region, and at the wall the temperature, let us say the temperature is Tw, and we approximate this as Tu, the unburnt temperature. So, if you are doing the experiment on room conditions, this temperature is probably 300 Kelvin. So, we are saying that the wall is at 300 Kelvin. Okay, not exactly correct, maybe slightly higher than that, because the flame is in touch with it, but let us say it is Tu, and here this is flame temperature Tb, burnt gas temperature. So, as a first approximation, you can write the dT dx at the wall to be Tb minus Tu divided by maybe d by 2. This distance is d. Okay. But that is like assuming a linear temperature profile. That is like saying that this temperature here is some Tb and this is Tu. So, you just draw a straight line, then you calculate Tb minus Tu divided by d by 2. Okay.
So
K is for the gas, K is not for the wall. Okay, K is for the gas. Now,
in case of gas, there is a convection.
here we are actually talking about, primarily we are talking about heat loss through conduction, and also this is also like a stagnant mixture. Okay, because remember how we talked about this mixture, that you have this fuel air mixture which is flowing, and then you have the flame on the top of that two plates, and then you stop the flow. So, it is essentially a stagnant mixture, but the flow has actually been stopped. So, the primary effect is actually conduction through the wall. Now, convection can be also an issue. The other point is that we cannot say that the temperature profile will linearly go down like this, because all through this region the flame exists. So, all through this region we expect the temperature profile, temperature to be high, is not it. So, drawing it again, you expect temperature to be actually close to Tb and then suddenly drop near the wall, right. If the flame is around here, then somewhere in the middle of the spacing, at the midpoint of the spacing, temperature will definitely be Tb. But if you say that it goes from Tb to Tu just like this, that will not be correct, right, because all this region you have the flame. So, that will have a high temperature, that will be close to Tb, only very near to the wall the temperature will start coming down. Okay. So, this is Tu. So, if you say dT dx is actually Tb minus Tu divided by d by 2, that is not correct, that is like a linear assumption. If you see this is more realistic, and if this is more realistic, we will expect the dT dx at the wall to be much higher than this expression tells you. Okay. So, to take care of that, we will take dT dx to be Tb minus Tu divided by d by b, where b is greater than 2. Okay. So, using this, going back to the equation that we had few minutes back. So, we had this equation, and the heat generation rate per unit volume can be written as minus m dot f triple prime bar into delta H c. All right, we know that from the analysis that we were doing for a premix flame, a planar premix flames, we were doing that when we tried to derive expression for SL, laminar burning velocity. So, minus m dot f triple prime bar dot delta H c, that is your q dot triple prime. Okay. So, why do we have the minus sign again?
Conjunction of
Yeah. So, the delta H c, now we have del d, we are going to looking at this delta dl equal to, so this is magnitude of dt dx that we want to use here. So, the magnitude, so we write k to delta L, and the magnitude of dt dx we write as Tb minus Tu divided by d by b. Okay.
what is the reference of x here, sir, from this direction to this direction?
Yeah, so actually that does not matter, we are taking the magnitude of dt dx. Okay. So, Tb minus Tu, so Tb minus Tu divided by d by b is what we are using at the temperature gradient. So, this is what we are trying to make sure that this is a positive quantity. The left hand side is a positive quantity. Okay. So, this also has to be a positive quantity, right. So, if you had the x going into the wall, then it is actually minus Ka dt dx, all right. So, if your x is like this, then the heat loss is minus Ka dt dx, and the dt dx is actually Tu minus Tb divided by d by b, because Tu is downstream, Tb is okay. But we actually just need the magnitude of the heat loss. So, we write k into 2 delta L into magnitude of dt dx. So, the magnitude of dt dx we are using as Tb minus Tu divided by d by b, b is greater than 2, to take care of the fact that it is actually not a linear temperature variation from the middle of the spacing to the wall. So, if you do all this, then this is the expression that we are getting. So, this is a limiting situation, this represents a limiting situation when heat generation is equal to heat loss. This is also known as Williams criterion. So, Williams gave this criterion. So, this is also listed in Turns's book as Williams criterion for this quenching situation. And we can, with the help of this, you can see that okay, we can actually cancel a few things, plus minus m dot f triple prime bar can be written in terms of SL, because we have SL equal to square root of, what was the expression, minus 2 alpha nu plus 1 m dot f triple prime bar divided by rho u. So, we had all that. So, if you look at this, then what we will do, and I will not do the steps here as such, using this one we can get m dot f triple prime bar in terms of SL. So, that can be used here, and for delta Hc, some time back we derived this. Okay. So, the m dot f triple prime bar will now be written in terms of SL, delta Hc will be nu plus 1 Cp Tb minus Tu, and then you have these other things. So, based on all that, you will be able to write d, and d can be shown to be equal to square root of b into delta with a little bit of work, which I think you can take care of.
So, this delta Hc will be for adiabatic flame?
Delta Hc expression that, yeah, that is correct. So, this is also an approximation. Delta Hc expression that we wrote is actually we derived it for an adiabatic situation, right. So, this here, so his point is, the question, his point is that the delta Hc expression is we are writing it as nu plus 1 Cp Tb minus Tu, that we derived for an adiabatic sort of situation, isn't it? But, and this is not adiabatic, but as an approximation we are using this. So if we use this, and if you also use the SL expression, SL expression is also for adiabatic situation, right? Overall SL is actually for adiabatic situation, correct? So it's not just delta Hc. So we are using these things, even though there is heat loss taking place from the flame. So as a first approximation, we'll be able to get d equal to square root of b into delta after you do this algebra. Okay, few things will get cancelled. Delta Hc as Tb minus Tu, and in the previous expression, the one that we want to use, the one which we want to simplify, that Tb minus this, that also has Tb minus Tu. So the Tb minus Tu's will get cancelled, and few things will happen like that, and you will be able to show that d equal to square root of b into delta. Now, is this useful? Not very useful, because you can't really actually calculate the quenching distance, because you don't know b. All that you know about b is greater than 2, maybe much more than 2. Okay, but you don't know the exact value of b, because the exact value of b you can get only if you have detailed measurements of temperature in the flame zone. Then you will know how temperature from the center of the channel goes towards the wall where it comes to Tu. So you don't have that information. Neither do you have a more detailed theory which tells you how temperature will vary near the wall. You don't have that. All that you know is b is greater than 2 and d equal to square root of b into delta. So if this is not very useful, then why did we do it? We did this because it, at least this tells you that this is linearly proportional to the flame thickness, and it also tells you that d is significantly greater than delta, because even if you take b equal to 2, then it's like 1.4 times delta, okay, but it's actually more than that. So it has limited utility, but it does give us something. Now if you look up different combustion text, if you look up Turns's book or somebody else's book, you will see some values of quenching distance. Now quenching distance is an important thing to know. Now just as an example, quenching distance for acetylene stoichiometric mixture is at ambient conditions is 2.3 mm. Okay. For methane it is 2.5 mm. For propane it's about 2 mm, and for hydrogen it is 0.64 mm. So we are talking about stoichiometric mixture of hydrogen and air with the mixture at ambient conditions. The quenching distance is 0.64 mm, whereas for methane it is 2.5 mm. All right. Now, can we actually interpret this from d equal to square root of b into delta? Does it help us interpret the values that we got? Don't have to remember the values as of now. You can always look these up from the book. But what I'm saying is methane has 2.5 mm, whereas hydrogen has 0.64 mm. Significantly less for hydrogen. So why is it so much smaller for hydrogen? Can that come out from d equal to square root of b into delta? Delta will be smaller for hydrogen. Now what do we know about delta? We derived delta as an eigenvalue from our premixed flame one-dimensional analysis. Okay. So we got m dot double prime and delta both from that analysis, and from m dot double prime we got SL, and delta was 2 alpha divided by SL. So SL is large for hydrogen. Now why is laminar burning velocity large for hydrogen, and how large it is? For stoichiometric hydrogen air mixture at 1 atmosphere 300 Kelvin, the burning velocity is more than 2 meters per second, whereas for methane it's like 37 centimeters per second. For other hydrocarbons it's 40, 42, 43, 44, 45 centimeters per second, whereas for hydrogen it's more than 2 meters per second. Hydrogen has larger burning velocity because burning velocity is, we understood, it's square root of alpha into reaction rate, even from the simplest theory, Maillard and Le Chatelier. Now hydrogen has small molecule, so it can diffuse easily, so it has high mass diffusivity, and it also happens to have a high thermal diffusivity. So alpha is large. Okay, alpha is large, and hydrogen reaction is also very effective. Reaction rates are high. So square root of alpha into reaction rate is high for hydrogen. So that's why people are sometimes afraid of hydrogen, because hydrogen is very reactive and also diffuses very easily. Now, because of high diffusivity, because of high reaction rate, hydrogen gives you high burning velocity, and the high burning velocity also comes with a low reaction zone thickness. Flame thickness is smaller if the burning velocity is higher, because the reaction is getting completed more quickly, correct? So we expect delta to be small for hydrogen, and if delta is small for hydrogen, then the quenching distance will also be smaller. So that's why 0.64 mm for hydrogen, whereas for methane is about 2.5 mm. Okay. Now are these values important? D equal to square root of B into delta, I told you that it has limited use, except helping you understand conceptually. In this case, it helped you understand, compare different quenching distances. But the quenching distance values that I told you, actual numerical values, that are also important, because if you're designing a burner, then you need to know, how large the passages should be. If you want to quench the flame, for example, for some reason if you want to quench the flame, then it's good to know these quenching distances. For example, if you have a burner somewhere, any kind of burner, not necessarily a tube burner, then probably somewhere upstream you have a mixer. So this is a mixer. So maybe you are supplying fuel there, and you are also supplying air. So the fuel and air mix here, then the fuel air mixture comes out of this, and then it burns on the top of the burner. Okay, so you got some flame, right? In case something happens, the flow rate is stopped and some disturbance in the flow, okay, something gets choked, then the flame can travel back, right? We know that. We have some understanding now. We don't fully understand, but we understand that when there is a flow, you can probably keep it stabilized on the top of the burner. When the flow stops, maybe the flame can travel back, because the flame has its food here, okay, all this region. So it will tend to consume that. Okay, you may not like it traveling back, but it will still have a natural tendency to do. And if it goes to the mixer, then it got a large volume. It has got a large volume of fuel air mixture which it can ignite, and that can be problematic. If it suddenly, it just travels and comes and reacts very strongly in a chamber which has mixing, which has fuel air mixture both coming in. So that can be problematic. That can lead to accidents. So there are actually flame arresters. There are flame arresters which are available in the market. Now, flame arresters will typically have some kind of a matrix with holes. Okay, I have just shown 5 here, but it will have hundreds. Right? So it's a matrix with large number of holes, and those holes will be tiny, and that sort of a flame arrestor maybe you can place here. Correct? So if the flame tries to travel back, then it will get quenched. Why will the flame get quenched? Because it's now no longer getting the full passageway. It is forced to travel back through large number of narrow passages, which you have created in that flame arrest. So the flame will get extinguished. So this is commercially available. And if we are doing a lab experiment, let us say, sometimes in IIT we don't buy these flame arresters, we can make our own flame arresters also. If you have wire meshes, and if you keep, let's say, 3 or 4, maybe even 5 or 6 wire meshes of appropriate mesh size, and if you keep one on top of the other, typically the open spaces of one will not match with the open space of the other. So it will give a complicated flow path if you keep them one on top of the other. That will make it even more difficult for the flame to propagate, and you will get quenching. Right. So this we can make a homemade flame arrestor. So this uses the idea of quenching. All right. And we can, since we know that d equal to square root of b into delta, can we also say something about the quenching distance for a given fuel? So we just compared quenching distances of different fuels, but if you have, let's say, methane air mixture, and if you vary the equivalence ratio, in which case do you think quenching will be more difficult? Yes, stoichiometric mixture will tend to have larger burning velocity, close to stoichiometric is larger burning velocity, and if you have a larger burning velocity, so in the last class we discussed this, right? We said that okay, laminar burning velocity is going to depend a lot on the mixture that you have, so it will depend on the equivalence ratio, and the equivalence ratio near stoichiometric will give you high adiabatic flame temperature, and high flame temperature typically leads to high burning velocities. Okay. So if you have a stoichiometric mixture, SL is high, delta is smaller, and if delta is smaller, then the quenching distance will be smaller. So if you know you are dealing with a stoichiometric mixture, your flame arrestor need to have smaller holes, right? Okay. So this is about quenching. Now we spent a lot of time on this, but we want to spend maybe a few minutes now on another concept, which is flammability. Again, this is something which even before doing the combustion course you kind of know of. So you know that if you have a fuel air mixture, there are flammability limits. I think all of you have studied internal combustion engines and in the undergraduate, and you must have come across concepts like this, okay, flammability limits. So if you have a fuel air mixture, the mixture is quote unquote flammable for some mixture ratios. So if the mixture is too lean, it's not flammable, and if the mixture is too rich, then also it's not flammable. So there is a rich flammability limit, there is a lean flammability limit, or in other words, there is an upper flammability limit and a lower flammability limit. So these things exist. So if the mixture is not flammable and you are trying to run an engine with that, or you are trying to burn that fuel air mixture on a burner to do some heating or something else, some other application, right? So then it will not work out. So the mixture has to be flammable if you're using it for combustion purposes. So the mixture has to be flammable. Now I said that okay, if the mixture is too lean, then it's not flammable. So we call it lean flammability limit. But then what is flammability? But how do we determine flammability? That should be the question. That should be an objective. So in this case, we will not be able to do an analysis. Like for quenching, we did a simple analysis and we got d equal to square root of b into delta. For flammability, we will not be able to do something like that. But I can tell you about how experimentally flammability is determined. Okay, so we'll start with that. So what is done is people take a glass tube which is mounted vertically. All right, so this is vertically mounted, and this is a glass tube so that you can see it has a fuel air mixture, and this is a standard flammability setup where the internal diameter is 51 mm and the length is 1.5 meters. Okay. So it's filled with a fuel air mixture. Now in a standard experimental setup, it's closed at the upper end. So, this is closed and this side is open, and it's ignited at the lower end, that is at the open end. And then what is flammability? You would like to see whether it actually propagates all the way up, right. If it propagates all the way up, then it is a flammable mixture. So, this is a simple setup. So, we are not discussing an analysis of flammability limit, we are not writing equations, we are not getting expressions for equivalence ratio for which it will get extinguished. That is too hard to do in the first course, but I just told you about how this experiment is done. This is a standard flammability setup.
How are you sending air fuel mixture here?
It is filled up with a fuel air mixture, filled up with a fuel air mixture. So, you can fill it up and maybe then open the bottom. Alright, so this appears simple, and this is a appears that there is nothing in it. Tube, transparent tube, fuel air mixture, ignite, just see whether it propagates or not, then it is flammable, otherwise it is not flammable. Okay. But where is the science? Does it have any science? Why is the internal diameter 51 mm? You can ask that. Has it come through some research? Yeah, so if we kept a tube which is 2 millimeter diameter and filled it up with a fuel air mixture, do you think it would have worked? Because even a stoichiometric mixture would not have been able to propagate in a tube of 2 millimeter diameter. It would have got quenched. Okay, so it's intentionally 51 mm so that the effect of heat loss is not very large. So, you are not trying to quench the mixture, you are not trying to quench the flame. So, you have intentionally kept it large. 51 appears to be, through trial, people have seen that 51 is good enough. At 51, you are not weakening the flame too much. Okay. So, this tells you that we want to get the flammability limits such that those are not unduly pessimistic limits, in the sense that if you keep it, as I said, very small diameter, then almost everything will get quenched. Okay. So, you do not want that information. That information is not good, because often quenching is not the purpose. So, we are doing experiments, we are actually using that fuel air mixture for some purpose on some burner or engine or some furnace or somewhere, right. So, why do you want to keep that diameter small? You do not want to do that, isn't it? You do not want to come anywhere close to quenching. So, this is why it is 51. Okay. Why it is 1.5 meter? This is also to have a length which is sufficient, okay, but not too large. As the flame moves from bottom to top, it will keep losing heat, but if you keep 10 meters, that's not very realistic. You want to see whether over a reasonable distance whether the flame can propagate or not. So, that is why it is 1.5 mm. This is another important aspect. Why are we igniting at the bottom? We are igniting at the bottom, and that ensures that the flame is propagating up. So, this is upward propagation. So, we have to know why upward propagation is used to determine flammability limits. You could have used downward propagation, that is, you again take the same fuel air mixture, ignite it at the top, flame propagates. But why do you want to do upward propagation? So, everything has a scientific basis. Any guesses as to why we want upward propagation?
Safety will help in.
Yes, yes. So, in case of upward propagation, there is, I mean, if the flame is going up, then because of the buoyant effects, the hot gases which are produced in combustion will be able to heat the unburnt mixture which is ahead of the flame, above the flame, more effectively, right. So, you would expect what? That upward propagation is easier, isn't it? Just intuitively, upward propagation will be easier. because it will be able to heat the mixture and transfer the radicals. Buoyancy will help in some way. Okay. Upward propagation will be easier. So, upward propagation will give you these flammability limits which are wider. If we use the upward propagation, we are going to get wider limits. Now, why do we want to get wider limits? Safety. Well, that is a good answer, safety. From safety point of view, if you have a fuel air mixture and you are preparing a database for flammability, let us say there is some new fuel which has come and you want to find out what is flammability. Of course, you would like to do experiments to give conservative estimates, because somebody has to use the data. So, from safety point of view, it is always better you tell them that okay, this mixture is flammable in this range for upward propagation. For downward propagation, for some limiting values it may not propagate, it may not be flammable, but you use an upward propagation experiment information so that people take care of safety. That is the logic. Okay. And some one or two other small points is that flammability limits, of course, as I mentioned, there is an upper flammability limit, there is a lower flammability limit, and which is like upper means higher value of equivalence ratio and lower means the lower value of equivalence ratio, or you call it rich flammability limit and or maybe lean flammability limit. Just to give you examples, for methane the lower limit is 0.46 equivalence ratio. So, if you have a equivalence ratio of about 0.5, mixture methane air mixture is still flammable, atmospheric conditions. Okay. And if you have equivalence ratio of 1.64, 1.64 is a rich mixture, right? 1.64 is a rich mixture, less than 1 is lean mixture. So, 0.46 is lean mixture, 1.64 is a rich mixture. For rich mixture, you can go up to 1.64 for methane. And for hydrogen, lean limit is 0.14. Okay, 0.14 also hydrogen air mixture is flammable. And on the other side, rich mixture 2.54 is the highest value of equivalence ratio of hydrogen air mixture in ambient conditions where the mixture is flammable. So, you see that hydrogen has much wider flammability limits, again for the same reason, that basically it is a strong fuel in the sense that it is highly reactive, it has got high value of diffusivity, so it can propagate easily and things like that. Okay. Now, what are the effects of various things on flammability if you increase the temperature of the mixture? See, the values that I gave you just for ambient conditions. If you increase the fuel air mixture temperature, then you expect that the flammability will increase, isn't it? Because the reaction will be easier. So, with temperature it usually helps and the flammability range will get widened. And pressure has much less effect. For lean side, actually it does not have much effect at all. For rich side, there is some effect. For rich side, upper limit gets enhanced, the lower limit does not get enhanced. The lower limit does not get affected much with pressure. Okay. We can't do much more analysis of flammability, but this is based on experiments. So, in the next class we will talk about ignition. So, we discussed quenching, there will be some similarity in the opposite sense. When you are talking about ignition, as I said, again transient, again we will use a limiting sort of analysis. So, stop here, we will meet tomorrow. Thank you.